স্টার্ট করো নাকি প্রদীপ? দেরি করে কি হবে?
প্রিন্সিপাল স্যার স্টার্ট করব?
হ্যাঁ, স্টার্ট করো।
ওকে। আচ্ছা, আজকে আমাদের মধ্যে যিনি আছেন ওনার নাম হচ্ছে প্রফেসর বিশ্বজিৎ মন্ডল। হি ইজ ভেরি ইয়াং and I know him personally, and he received his BSc from Scottish Church of College and his master degree from IIT Kharagpur, PhD from Indian Association for the Cultivation of Science, IACS, and he has research experience. In 2017 he joined the Department of Chemistry at the University of Wisconsin-Madison, USA, as a postdoctoral fellow to work a great scientist, Professor Samuel. And then he did his second postdoctoral work from Ben Gurion University, Israel. And he recently joined at IIT Gandhinagar as an assistant professor. His research interests include photoelectrochemistry, electrochemical conversion of value-added chemicals, renewable energy, and spectroscopy. And today he will present an interesting topic, electrocatalysis in chemical value addition. তো তার আগে আমরা প্রিন্সিপাল স্যারকে অনুরোধ করব এবং ওনার পারমিশন নেব আমাদের প্রেজেন্টেশন স্টার্ট করার আগে। আমাকে বলবো কিছু বলার জন্য। নমস্কার স্যার।
হ্যাঁ, থ্যাংক ইউ প্রদীপ। আমি আবার বাংলাতেই বলি, কারণ আমার মনে হচ্ছে প্রায় সবাই আমাদের বাংলারই ছেলে। আমরা প্রথমেই প্রফেসর বিশ্বজিৎ মন্ডলকে আমি আমাদের কলেজের এই অনুষ্ঠানে ওয়ার্ম ওয়েলকাম জানাচ্ছি, তাকে স্বাগতম। আমার আন্তরিক শুভেচ্ছা, অভিনন্দন। আমি যেটুকু প্রদীপের কাছে শুনলাম, ইজ এ ব্রাইট ইয়াং ফেলো, ইজ এ ভেরি প্রমিসিং সায়েন্টিস্ট ইন দি ফিল্ড অফ কেমিস্ট্রি। আমাদের মধ্যে একটা ছোট্ট কলেজে এই ধরনের একটা স্পিচ দেওয়ার জন্য তিনি রাজি হয়েছেন। এই জন্য তাকে আমাদের কলেজের সবারই তরফ থেকে, বিশেষ করে কেমিস্ট্রি ডিপার্টমেন্টের তরফ থেকে আমি আমার আন্তরিক ধন্যবাদ, আমার কৃতজ্ঞতা প্রকাশ করছি। আমি আমার বক্তব্যকে দীর্ঘায়িত না করে আজকের এই ওনার স্পিচটা আমরা মন দিয়ে শুনি। সাবজেক্টটা আমার কাছে একদমই নতুন, যদিও আমি ফিজিক্সের ছাত্র, তবুও কিছুটা জানা তো দরকার সবারই। আমি একদমই কিছু জানি না এই ব্যাপারে। তা আমি প্রথম দিকে কিছু নিশ্চয়ই শুনবো। প্রদীপ, এবার আমরা শুরু করি, ওনাকে আমরা অনুরোধ করি আজকে। থ্যাংক ইউ ভেরি মাচ।
শুনতে পাচ্ছেন সবাই?
হ্যাঁ, পরিষ্কার শোনা যাচ্ছে।
Yeah, so thank you, Principal Sir, for this warm introduction, and also Professor Pradeep Kumar Das, famously known as PKD, for inviting me, to deliver this lecture. So as I'm told, it's kind of a tutorial seminar. So আমি মানে যেখান থেকে শুরু করব সেটা হচ্ছে খুবই basically. And then from there, I will just, as you can see, the topic is electrocatalysis and chemical value addition. So we'll start very basic of electrochemistry, and then we can discuss about why this electrocatalysis is still relevant in modern day life. And from there, I will just walk you through the kind of research that I'm doing at IIT Gandhinagar. And as you know, I just started my group, so there is not much development in the research front, the independent research front, but I would like to share my goal or kind of research I'll be doing at IIT Gandhinagar. So without much ado, let's begin. So as you can see here, the topic is electrocatalysis and chemical value addition. And so So before going into this electrocatalysis, so first we need to learn like what is electrochemistry, right? And as you can see, the terminology that is electrochemistry, that means it has the role of electron dealing with chemistry, or you can say that electrical energy dealing with chemical energy. So basically in electrochemistry we study the interconversion between chemical energy and so basically we study the interconversion between chemical energy and electrical energy, and we can easily do so by looking at the spontaneity of the reaction. So this is a very basic thermodynamics, that is if the kind of a delta G is a free energy change of a reaction, and it's kind of a signature value. If it's less than 0, then the reaction is said to be spontaneous reaction, and whereas the delta G is greater than 0, then the reaction is said to be a non-spontaneous reaction. And the spontaneity plays a critical role in determining in which way we are moving. So whether we are moving from chemical energy to convert it to electrical energy, or the other way around, that the electrical energy to the chemical energy. Right? So before going into the much scientific part, let me tell you a story, like how this electrochemistry or the entire subject has been developed. So and I would also request you, so while you listen to the story, please remember the timeline. So as you can see here, it's around 1780. There is an Italian scientist, Luigi Galvani, and his wife. তারা কি করছিল, মানে ব্যাং নিয়ে তারা কিছু অ্যানিমাল ইলেকট্রিসিটি নিয়ে রিসার্চ করছিল. সো ফর দ্যাট they tied this frog leg with a metallic wire, right? And accidentally or incidentally, there happened an electrical spark, where they observed that with the electrical spark, these legs are twitching, like in pata nore utlo. And with that observation, and as you can see here, it's only 17th, 18th century. That means no such scientific theorem or those things were there, right? So with this observation, they concluded that this twitching of frog leg is due to the animal electricity, right? And Galvani shared his view with one of his friends, that is Alexander Volta. I believe like you must have heard his name. And Volta initially Galvani jeta bolechilo je this is because of this frog leg twitching is because of animal electricity. He initially believed that, but however he tried investigating this thing further, and consequently there are the other observation, like electric field এর সাথে magnetic deflection or the heating effect of the electricity, like when the electricity is passing through a metallic wire, it's associated with some of this heating effect. And also you can, with this electricity, you can also perform chemical change. So these are the observation which kind of instigated Volta to believe that whatever Galvani is proposing as the reason of twitching of this frog's leg is due to animal electricity is not right. But he didn't came up with concrete proof of it. Okay, so he started investigating this thing further, and then he came up with this contact theory of electricity. So to disprove that whatever Galvani's observation of frog leg twitching is due to this. Okay, just a minute. Is my slide still visible?
Yes, it's now visible.
It's page 6 now, right?
Page 6, yeah.
Please show page 2 to 6 once. Yeah.
Yes, now.
This is 1, 2, right?
Yes.
Okay. So yeah, so So to give a concrete proof that whatever Galvani is proposing, the twitching of frog leg is not due to any animal electricity, Volta come up with this contact theory where he basically piled a copper and zinc. You can see this is a copper and zinc, and in between he placed a brine soaked cardboard. I will come to that later, why he selected copper and zinc. There is a specific reason to it, and with this he can show that yeah, there is a passing of electricity, and your frog leg is not necessary, right? So the idea of animal electricity was discarded by the invention of this Volta's contact theory based on this copper and zinc plate. And not only that, this whatever assembly you can see here is termed as voltaic pile and is the simplest form of modern day battery. Okay. And to give his friend a credit, because ultimately it was his friend's observation, that is, it was Galvani's observation, the process is known as galvanic process. So the pile is known as voltaic pile because Volta discovered this, but the phenomena is known as galvanic process. To give due credit to the Louis Galvani, who first observed this thing. And as you can see here, like then it further developed, and then there's a scientist Anthony Carcel, who first, with the help of this voltaic pile, did a water splitting reaction to form hydrogen and oxygen. And I'm telling you this because, so this is, so you can see here, it's around 1800 AD. So this is the reaction that has been already been developed around that time. Okay, and around 1801, Humphrey Davy came up with this fuel cell technology. But if you see that's, even at the 2022, people or the scientists all over the world are looking for a good catalyst for water splitting to hydrogen, and also to use that hydrogen in a fuel cell technology. Now you must be wondering that, so you can see that those processes are developed quite a long back, right? 1800, like almost 200 years ago. So, but the problem was that, so the time it was developed, there is no such market, right? তখন ওনাদের মতে এইটা ছিল না যে around this 2000 AD there could be a scarcity of fossil fuel, or there might be a very pronounced effect of global warming, right? So they discovered, and since the market was not there, it was at its infancy. But now at 2020, people are realizing that these are important processes, and that's why people are gaining renewed interest to pursue electrochemistry or electrocatalysis, particularly in the energy field, like fuel cell or water splitting into hydrogen and oxygen, right? And then around 1834, then Michael Faraday came, and he gave some of this very crucial law for electrolysis, right? How the mass balance is conserved and everything. Okay, and he is also considered as the father figure of modern day electrochemistry. And in the very next slide, I will show you a very interesting thing, that if you follow the timeline, you see that so far we're discussing about electrochemistry, that means passing of electron and converting electrical energy into chemical energy and chemical energy into electrical energy. But as you can see here, all the key formulas or hypotheses were developed around 1834, right? Even the fuel cell and the water splitting technology is developed around 1800 AD, but it's only around 1896 AD that J.J. Thomson discovered electron, right? So this is kind of a surprising, and this is kind of a very inspiring to me as well, that how this intuitive thing can give you or lead you to important discovery without actually knowing the particular thing that is associated for this particular process. In this case, it is electron. So as you can see here, electron is discovered around 1896, but all the major laws of electrochemistry, as you can see here, is almost pretty much done around 1834 AD. So this is kind of a remarkable thing that I personally feel that you should give a proper emphasis on. So yeah, enough of history. So now if we see that, okay, what's happening right now, like let's say around 11th of June 2022, if you see here is that, we are all surrounded with some of or other kind of application of this field, electrochemistry. So as you can see here, the very basic thing is the battery, as I told you, is kind of a modern day voltaic pile. And you see that you're surrounded or you are connecting or you are taking part into this video conference with some of these devices that uses this battery. You are using your mobile phone, you are using earphone and all, and everything, everywhere it requires a battery, right? So everywhere you are surrounded by electrochemistry. So this is the kind of impact electrochemistry has in our more day-to-day life. And also, you must be aware of that India is currently the most prominent market for EV, right? So you can think about this EV vehicle and all. That's also uses this battery thing. That's kind of a derivative of electrochemical technology, and this is the kind of a way forward. Okay, so as you can see here, this is the timeline. So this is the and around 2050. So we are targeting that all our transportation and everything will be converted to the sustainable future technologies. That is either to this renewable fuel cell hydrogen or this EV thing, right? And there is a catch though, that so we can think that, okay, so whatever fuel thing we can replace with the green fuel, right? So if we're using petrol, gasoline, diesel, we can easily replace this thing with hydrogen or some other technology, right? But there is also a downstream petroleum industry that which are kind of heavily been practiced, that is the use of the small aromatics, right? Like BTX or kind of benzene derived product. So those are also coming from petroleum industry, right? So for transportation purpose, okay, there is a feasibility that we replace this gasoline or diesel with hydrogen. But what about the other thing? Like how you replace the downstream petroleum industry with something sustainable? So, so my today's talk will be based on this particular topic, that how we can do value addition to a chemical feedstock, as well as we get hydrogen through simple water electrolysis. Okay. So as I was discussing so far, so the application of electrochemistry only in the energy sector, but this is not the case. This is just a very small slice of the pie chart. But as you can see here, electrochemistry is applicable to anywhere. Like, so you can think of like the modern day researchers are thinking about applying electrochemistry in organic synthesis. So I will give you a very simple example. Like in most of this organic reaction, suppose you are doing alcohol oxidation or to aldehyde or acid, or aldehyde reduction or nitro reduction. So basically you are doing an oxidation reduction reaction, and wherever you are doing an oxidation reduction reaction, it's always useful that you use electrochemistry, because through electrochemistry you can very easily give electron or take out electron. That is basically you carry out reduction or carry out oxidation very easily, right? And the advantage is you don't need any stoichiometric oxidant. So suppose you are doing some alcohol oxidation to acid, or some toluene oxidation to, let's say, benzoic acid. So you require a stoichiometric oxidant, right? So you will generate a stoichiometric waste. But if you use this electrochemical technology to oxidize or reduce your substances, so since it's kind of catalytic in nature, so you don't generate a stoichiometric waste. So there's a clear advantage of invoking electrochemistry in organic synthesis. And also this electrochemistry is used in various of sensors application, like you use a glucometer, that's basically an electrochemical sensor, and it's heavily being used in inorganic synthesis, and it's the large portion of this is kind of chloralkali manufacture or kind of metal extraction and the metal you are using in day-to-day life. So the essence of this slide is that so electrochemistry is not only applicable for this energy to solve energy problem, but you can use electrochemistry to solve like various other problem where this electron transfer thing is involved. Okay, so now going back to my first, I think the second slide, where I discussed that the spontaneity plays a key role in deciding the factor that whether we'll be moving from chemical energy to electrical energy or electrical energy to the chemical energy. And I already discussed about this galvanic cell. So just try to recall that galvanic cell is the pile between a copper and zinc, right? So copper and zinc, and then you are getting an electricity. That means you are converting chemical energy into electrical energy. And if this process is spontaneous, that is delta G is less than 0, then the process is thermodynamically favored, and you will see that kind of a galvanic cell is formed, where you spontaneously transform chemical energy into electrical energy. So basically, all the batteries you are seeing, that's kind of a galvanic cell. And there is another kind of cell where we supply electrical energy to perform chemical conversion, and that is called electrolytic cell. So my current talk is mostly based on this electrolytic cell. So as I was discussing about water splitting reaction, so you need to break water molecule into hydrogen and oxygen, right? And for that, it's kind of a non-spontaneous process, thermodynamically unfavored. So that's why you have to supply electrical energy to carry out this splitting to get the hydrogen out. Okay, so now how do you know by looking at the reaction whether the reaction is spontaneous or non-spontaneous? Okay, so your obvious answer would be okay by looking at the delta G value. And the beauty of electrochemistry is that so this delta G is related with the electrode potential of the particular process. Okay, so there is a relation between your delta G and the E, that is the electrode potential. So before going into that relationship, let's understand that what this electrode potential is. So electrode potential is, suppose you have a copper or zinc and you place it in a copper sulfate solution. So it has a propensity of either giving out the electron or taking away the electron, right? So based on that, a potential is developed on the metal strip, which is known as this electrode potential. And if your whatever arrangement here is in standard condition, that is in 1 molar at 298 K and 1 bar pressure, if you're dealing with gaseous component, then the potential is termed as standard electrode potential, that is E naught, right? So those are the two key component of your electrochemical system. Okay, and from this, there's this electrochemical series where by looking at this E naught, you can say that if you make a pile, so suppose in voltaic cell, if you remember, it's a pile between copper and zinc, where the E naught of copper is 0.34 and the zinc is negative 0.76, right? And if you calculate the cell potential is kind of 1.10 volt, that is 0.34 volt negative whatever the zinc 2 plus zinc potential, right? And delta G, as I was telling before, is related to this E cell with this equation, that is delta G is equal to negative NFE. Now if you get this E cell positive, and if you just plug the E cell here, and N is 2, F is a Faraday constant, and you will get the delta G to be negative, right? So based on this electrochemical series, basically you can choose any of these two redox couple that will essentially give you a positive E cell value, and you can make a voltaic cell of your own, right? And the only criteria is that your E cell should be positive, and then only you will get the delta G to be negative. And when your delta G is negative, if you just club them together, your whatever chemical energy will be converted into electrical energy. That's the basic behind the galvanic cell, or the kind of a battery we are using. And if you're very away from the standard state, if you're away from this E naught, so there is a way where we can relate the E naught to the E. Yes, please. Okay. So
Sir, I have a question that spontaneity and non-spontaneity. I think all the reaction should be non-spontaneous.
So no, please ask question after that talk is over. Okay.
No, I'm fine. Like, yeah. So why do you think all the reaction are non-spontaneous? Shona? So the thing is that I will come to that activation energy barrier thing later. So spontaneity and non-spontaneity, that is, so thermodynamics decides whether the reaction is spontaneous or non-spontaneous. The spontaneous reaction, can have a activation energy barrier, which makes it look like that the reaction is not happening. But it's not that the reaction is not spontaneous. It's just that it may associate with a high energy activation energy barrier. Okay, so I'll come to that later. Yeah. So we can relate basically the E cell and E naught cell with a Nernst equation, and that's kind of a basic thing that you are being taught in your PhD curricula, I believe. Okay, so since we'll be talking about electrocatalyst, so let's first discuss like what is a catalyst, right? So we know enough about this electrochemistry, and we know about this electrode potential, spontaneity, and now let's talk about the activation energy barrier, which basically tells you the kinetic of the reaction. So suppose you have a uncatalyzed process, which you can see in the blue trace in the plot, okay, which obviously will have a high activation energy barrier, and this is kind of a non-catalyzed or uncatalyzed process. And if you have a catalyst, you can see that the activation energy barrier decreases. Now the reaction is become more facile. So nonetheless, in both for this red trace and the blue trace, the reaction is spontaneous. You can see that your del G is negative, no matter what. But with the introduction of the catalyst, you have a lower activation energy pathway, which makes the reaction more kinetically favorable. Okay, and you can think about this catalyst, in any of this field. Like, you can think about this biocatalyst. So you must be reading about this enzymes and all. You must be learning about this, some of this organometallic catalysis, which is kind of in the realm of homogeneous catalysis. But particularly we're interested in this today's talk is in the electrocatalyst. That means a catalyst which can be a window of electron transfer as well. Okay, so this is our area of interest, and we can just broadly divide catalyst in any of these 5 categories, to be honest. And so catalyst we know, like, and then let's talk about the reaction, like which reaction we want to be catalyzed. And as I was give you the introduction that we mostly talk about this either the fuel production or fuel consumption, because we are mostly concerned with the energy related problem. So these are the key reaction, that is proton reduction to hydrogen, or hydrogen oxidation to proton, or CO2 reduction to hydrocarbon, or hydrocarbon oxidation to CO2, or water splitting to oxygen and hydrogen. So these are the kind of reaction which is is either kind of fuel forming or fuel consumption reaction that we want to get catalyzed through our electrocatalyst. So let me reiterate what I have said. that we understood the basic electrochemistry. We understood the governing factor like del G and E, and then we know about the catalyst, and with those catalysts we want to catalyze this reaction because those reactions are relevant for energy application. Okay, and as I was talking about this E naught value, so all this reaction will have a particular E naught value. Like for example, for proton reduction to hydrogen, the E naught value is set as 0 volt. Whereas for carbon dioxide reduction to carbon monoxide, the potential is around negative 0.11 volt. And similarly for O2 reduction to water, the potential is around 1.23 volt. So each reaction, each redox reaction is associated with a particular E naught value. Okay, so E naught means the standard electropotential that I already discussed. Okay, so and the thing is that I want to catalyze this reaction. Right, so these are the reactions. This has a particular E naught value, and I want to catalyze this reaction with the help of a electrocatalyst. So, like any other catalyst, electrocatalyst should have this figure of merit, right? So you cannot work with any catalyst. Your catalyst should have some qualifying criteria through which you can differentiate between a good catalyst and a bad catalyst. Of course, you don't want a bad catalyst to run your reaction. So this is the kind of a figure of merit to understand how good is your catalyst. So the first thing we discuss is the activity, right? So that if the activity is better, your catalyst is better. So you have developed a better catalyst. And activity is decided based on this two factors. One is overpotential. I will come to that term later. And another is the turnover frequency. So turnover frequency is nothing but rate of the reaction. That's the kinetics of the reaction. And overpotential deals with the thermodynamics. I will come to that specific term a little later. And so this is more or less the activity. And stability, as you know, like you want your catalyst to be reusable for many times, right? So for that, stability is also a crucial factor. And selectivity. Selectivity means, suppose in the previous slide you will see that suppose you want your carbon dioxide to get reduced to ethanol, what you can see here is that CO2 can be reduced to various of product. But if you want a selectively ethanol, then it has to deal with so your catalyst should have a property to tune the selectivity of the reaction, which is associated with the Faraday efficiency. Right? So this is the figure of merit, more or less. There is the activity, stability, and selectivity. So stability and selectivity, is kind of an intuitive. So I'll not discuss much about it. So let's discuss the activity part. And as I said, that activity has two terms in it. One is overpotential, and another is turnover frequency. So turnover frequency, don't bother much about it. Turnover frequency is just the catalytic rate. Means how fast you are getting the catalytic turnover. That is your turnover frequency. But the key term here is the overpotential. Okay. So to understand overpotential, let's understand like what's happening. Or how we see or analyze this electrochemical responses. So you see here this blue, black, and red traces. There is a specific technique called cyclic voltammetry, where this kind of a very basic technique to analyze the catalytic property of your catalyst, right? So suppose I am doing water reduction to hydrogen, right? If my water reduction to hydrogen is uncatalyzed, so I have to apply a large negative potential to reduce my water to hydrogen, right? But if I am using a catalyst, right, there's the black press here, and my catalyst is doing the water reduction to hydrogen, then I don't have to go to this large negative potential. I'll be able to catalyze my water reduction here only, right? Because I have a catalyst, and the catalyst will allow us a low energy activation energy pathway through which I don't have to spend this much of negative energy to reduce my water. With the help of catalyst, I can just reduce my water at a much lesser energy cost, right? So this is how we analyze. And so you must have read the chemical kinetics, where you have learned like if the reaction is first order with respect to the any of the substrate, then with increase in the substrate concentration, your catalytic rate will increase. And here also you see that with the cyclic voltammetry, as I said, that this turnover frequency is nothing but the catalytic rate, which we can easily follow by looking at the catalytic current we are getting. So as you can see, with the increase of the substrate concentration, let's say water, so if you are looking at water reduction to hydrogen, we'll see like more and more current due to water reduction to hydrogen. That okay, and if you plot the current with respect to the water concentration, we'll see that it will be a linear plot, and that will give some sense that about the order of the reaction. Okay, and this is kind of a combined thing. So okay, so now I determine the order of the reaction, and now let's say like here is my standard potential. There is the E naught of proton reduction or water reduction to hydrogen. As you can see here is the dashed line, red dashed line at negative 0.4 volt. Okay, let's say this is the E naught, and suppose you are seeing catalysis around negative 0.8 volt, right? So this is the so what does E naught signify? So E naught signifies is that this is the minimum potential if I have to apply to carry out this conversion. That's the thermodynamic minima, right? And the thermodynamic minima lies somewhere here. But you have to apply some extra energy to carry out this conversion. That is proton reduction or water reduction to hydrogen. And that extra energy you have to apply is termed as overpotential. Okay, and intuitively you can say that you don't want to spend this extra energy, and you know on the corollary you can say that overpotential, the lesser is the overpotential, the better is the catalyst, because that's the extra thing you are providing to carry out this conversion. Okay, and you can also get some sense about the rate constant of the reaction by looking at this catalytic current and all. So I'm not going into much mathematical treatment of it. And with this background, let's discuss like what I am doing here at IIT Gandhinagar, right? So I talked about this water splitting reaction, that is splitting of water into its gaseous component, that is water, that is oxygen and hydrogen, and it requires a thermodynamic potential of let's say 1.23 volt, right? So and that you can find from the standard hydrogen. Standard electrochemical series. Okay, so what happens here in the conventional water electrolysis system is that you have a cathode where reduction is taking place, and you have an anode where oxidation is taking place, where water is oxidized to oxygen, and in the cathode water is reduced to hydrogen. Right, but the problem is that this water oxidation process is kinetically very sluggish, and it requires a very high overpotential. That means you have to spend a lot of energy, extra energy I would say, to split or to break this water molecule into oxygen and hydrogen. And another added problem with this is that you cannot get a pure stream of hydrogen, because there is a possibility that whatever oxygen you are making in this compartment can mix, and that will lead to a explosive gas mixture. Okay, so you cannot use this hydrogen if a little amount of oxygen is mixed into the hydrogen gas. So to get rid of this, what we can do here is that we can use some biomass like lignin or some plastic waste like PET and do the oxidation here instead of doing water oxidation, and that will save us energy, because any organic oxidation require pretty less potential compared to the water splitting or the water oxidation to oxygen. And the added advantage here is that we can still get hydrogen at the cathodic compartment, and now there is no probability of mixing hydrogen and oxygen gas, because we are not oxidizing water to oxygen anymore in the anodic compartment. So you will get a pure stream of hydrogen here, and you will do chemical value addition of biomass or plastic waste on the anodic compartment. Okay, so for this, let's not go into much details about the actual structure of the catalyst. So we prepare a catalyst, so we deposited the catalyst on the electrode surface, and then we kind of decipher the mechanism of the reaction. Is that so if with the same catalyst, if we do water oxidation reaction, it will require very high potential. But with the same thing, with the same catalyst, if we do substrate oxidation or the organic substrate oxidation, because now we are dealing with weak CH bond, it's very easy to oxidize weak CH bond, and we are saving energy in terms of electrochemical technology, and we are also doing chemical value addition to whatever organic molecule we are oxidizing at the anodic compartment, and also we are getting hydrogen at the cathodic compartment. So everything is a bonus here. Okay, and as you can see here, like we analyze the methanol oxidation to format, and it's kind of got format as a kind of a single product, and it can operate at a very high current density and at much lower energy cost compared to the whatever is required for water splitting reaction. And we also demonstrated that is basically by changing the CH bond strength. Suppose you are going from this aliphatic CH to benzylic CH associated with the benzylic alcohol, and benzylic CH associated with benzylamine. You can see that with the strength of the CH bond scales linearly with the catalytic rate. So that means we will get more rate if we choose a very weak CH bond. Okay, and so this is a kind of a simple lab scale demonstration of oxidation of benzyl alcohol to benzoic acid, and you can see here is that since the benzoic acid is not pretty much soluble in water, so as soon as you make it, this benzoic acid flocculates from the mixture. So not only that you are making benzoic acid, which is a key component in the various industrial application, but also there is no separation cost involved, and as well as you are getting pure stream of hydrogen without any mixing of oxygen here. Okay. And we are kind of extending our studies to various other substrate oxidation, and the most key player in this is this lignin model complexes, or the lignin itself, where you can see here is that it's kind of a benzylic OH as well that we need to oxidize. And in the very beginning of my talk, I said that so it's not that we have to replace the hydrogen as a fuel, with the existing gasoline technology, but also we need to take care about the downstream petroleum industry dependence. So as you can see here, so we can, if we just upgrade lignin or upgrade PET waste, that's the polythene waste, we can get the small aromatic while getting hydrogen on the cathodic counterpart. So these are the kind of substrate we are trying to oxidize and simultaneously get hydrogen in the cathodic compartment. And another substrate that is worth mentioning is this hydroxymethyl furfural, that is this HMF here. And if you oxidize this HMF, you will get furan dicarboxylic acid, which is a platform chemical for nylon 6 synthesis, right? And also, we are kind of capable of demonstrating that this aniline can be directly oxidized to this azo dye, in the anodic compartment with the added bonus of hydrogen at the cathodic compartment. And if you look at this chemical technology for aniline to azo dye formation, you will see that these are like harsh chemical or require stoichiometric oxidant or reductant, which is kind of a problem in modern day green technology to solve this modern day green technology challenges. Okay, so with this, I hope I can do some interest in you in terms of electrochemistry and how relevant this electrochemistry or electrocatalysis is particular in our modern day life. And my research, as you can see here, is kind of a hybrid water electrolysis for this chemical value addition, and as well as simultaneous generation of hydrogen, because both are necessary if you want to look forward to replace a sustainable energy solution with the existing gasoline-based energy vector, right? And and we are also trying like several biomass and plastic waste so that we can just control this environmental issue as well. While pursuing this research. With this, I want to conclude and thank my lab members and my discipline of chemistry and the Central Instrumental Facility at IIT Gandhinagar and all my collaborators. So with this, I conclude and I'll be happy to answer any question if you have.
Okay. It's a nice presentation. Thank you, Vishwajit. Now, এখন হচ্ছে কোশ্চেন অ্যান্সার সেশন। যদি তোমাদের কোনো ডাউট থাকে তো প্রফেসর বিশ্বজিৎকে তোমরা বলতে পারো। হ্যাঁ, তখন তো কিছু জিজ্ঞেস করবে নাকি?
হ্যাঁ, প্রথমে আমরা ধন্যবাদ জানাবো, খুব ভালো লাগলো।
থ্যাংক ইউ
প্রফেসর মন্ডল। ছাত্রছাত্রীদের কিছু নেই কোশ্চেন? একজন কি বলছিল? একটা
সৌনক কিছু বলছিল।
সৌনক বলবে? আমার একটা ছোট কোশ্চেন আছে।
হ্যাঁ হ্যাঁ, শিওর স্যার।
হ্যাঁ, আমি জাস্ট ওই ইভি বা হাইড্রোজেন পাওয়ার ভেহিকল নিয়ে জানতে চাইছি, মানে what is going on in the latest models, what is the chemistry going on?
না, কেমিস্ট্রি লাইক যেটা তৈরি হচ্ছে যে আরো কম্প্যাক্ট,
রাইট যতটা ছোট করা যায়, যতটা ইজি করা যায়।
and the another problem is that like আপনি হয়তো শুনে থাকবেন নিউজ পেপারে যে most of the EV vehicles are not compatible in Indian atmosphere because ওখানে because
given the heat.
Exactly. তো ওইটা একটা কম্পোনেন্ট যে মানে যেটা ইন্ডিয়ান রোড কন্ডিশন টেস্টিং ছাড়া হয়ে গেছে। বেসিক্যালি কি হয়, একটা মানে চার্জ স্টোরেজের জন্য আর ডিসচার্জের জন্য একটা আয়ন মুভমেন্টের দরকার হয়, এবং ইন্ডিয়ার মোস্ট অফ দ্য রোডস আর বাম্পি, এন্ড তো ওই ফ্যাক্টরটা প্লে আউট করে ডিউরিং দিস চার্জ ট্রান্সপোর্ট, এন্ড দ্যাট ইভেন্চুয়ালি লিডস টু হ্যাঁ, তো এটা একটা সমস্যা ডেফিনেটলি। আদারওয়াইজ লাইক হাইড্রোজেন টেকনোলজি, লাইক government of India is also pretty much supportive.
Interesting.
এবং there are pretty much going on in this hydrogen field. Like so previously I was in CSIR, Indian Institute of Petroleum, and there is this Ministry of New and Renewable Energy Research, this shortly termed as seminary. ওদের ওখানে ওরকম মানে হাইড্রোজেন, of course it's diesel powered hydrogen generation, but you can have your hydrogen as a fuel in your vehicle. So ওদের হচ্ছে prototype vehicle they are testing, and so I would say like মানে personally আমি বলবো যে হাইড্রোজেন হয়তো eventually will come up, but definitely the current market is for EV. You will see EV taking over. And another thing is that India, of course, US say it changed out dramatic hobe na, because US or any other developed country they already existing infrastructure royeche, so they will not change their existing infrastructure, but as a developing country India অনেক স্কোপ রয়েছে, বিকজ অনেক জায়গায় রয়েছে ইন্ডিয়ার যেগুলো মানে প্রপার ইলেকট্রিসিটি যায়নি বা প্রপার পেট্রোল পাম্প, মানে গ্যাস নিয়ে যাওয়ার জন্য তো মানে পাইপলাইন বা এটসেট্রা লাগে, তো সেগুলো হয়নি। সো ইন দোজ এরিয়াস উই ক্যান থিঙ্ক অফ লাইক implement, like right from the beginning we start from the renewable thing, like EV or hydrogen or any other renewable energy based technology. So I think like as a developing country or a developing nation, India has more scope of implementing this renewable energy thing than any other already developed country in the world.
Absolutely.
স্টুডেন্ট তোমাদের যদি কিছু জিজ্ঞেস করার থাকে স্যারকে, আমার মনে হচ্ছে না কোনো স্টুডেন্ট আর কিছু জিজ্ঞেস করবে। এনিওয়ে বিশ্বজিৎ বাবু, খুব ভালো লাগলো লেকচার। থ্যাংক ইউ, থ্যাঙ্কস এ লট। হ্যাঁ,
Thank you, Biswajit, for your nice presentation, and thank you
এলে
everyone.
আসুন একদিন কলেজে।
Sure, definitely.
হ্যাঁ একদম।
পিকেডি হচ্ছে আমার মানে একদম সিনিয়র, মানে জাস্ট সিনিয়র,
আচ্ছা আচ্ছা,
এক বছরের senior.
এক বছরের সিনিয়র। হ্যাঁ, ইটস লাইক ভেরি হার্ড ওয়ার্কিং এন্ড ইয়া উই স্পেন্ট মানে অনেক সময় কাটিয়েছি আর কি একসঙ্গে ল্যাবে, মানে অলমোস্ট সমসাময়িক আর কি।
গ্রেট মেমোরিজ।
গ্রেট মেমোরিজ, ইয়া। এন্ড অফ কোর্স লাইক বিদ্যাসাগর কলেজে, মানে ওই কলেজ চত্বরেও আশেপাশেও অ্যাকচুয়ালি আমার কলেজ ছিল স্কটিশ চার্চ, তো নর্থ কলকাতার সঙ্গে একটা আলাদা বন্ডিং অলওয়েজ আছে আর কি।
কলকাতা এলে আসুন একদিন।
শিওর শিওর শিওর। ভালো থাকবেন। নমস্কার।
Okay, chalo,
হ্যাঁ নমস্কার, থ্যাংক ইউ।
thank you very much, Biswajit.
থ্যাংক ইউ পিকেডি।
Thank you too for having this opportunity, having us more on this opportunity.
মাই প্লেজার স্যার। লগ অফ করছি তাহলে।
Okay.
হ্যাঁ ওকে,
থ্যাংক ইউ সো মাচ।
প্রদীপ,
হ্যাঁ